this video, we're going to add two new rules to our list of derivative rules, specifically the product and quotient rules. So anytime we have a function that is a product of two algebraic expressions or a quotient of two algebraic expressions, in general, when we want to differentiate such a function, we're going to use the product rule or the quotient rule. So immediately when you hear product rule and quotient rule, you might be thinking sum and difference rule, and these are going to be similar to the sum and difference rules. If you recall, the sum and difference rules essentially stated that if you have a function that has multiple terms in it, either added or subtracted from one another, then you can differentiate term by term. So logically speaking, it might be reasonable to conclude that if you have a function that's a product of different expressions, then you can just differentiate each and multiply the derivatives together. Unfortunately, it's not that simple. So the derivative of a product is not the product of the derivatives. Unfortunately, it is not that simple. It's a little bit more complicated than that. Well, if it's not the product of the derivatives, if we can't just take one derivative times the other, then what will the actual derivative rule tell us to do? Well, here is the product rule. So given two functions, f of x and g of x, if we want to take the derivative with respect to x of f of x times g of x, then we apply the following rule. And here I'm using our Leibniz notation. I'm going to convert to the prime notation just to make the formula a little bit easier to use. So if we're differentiating the product of two functions, then the derivative is going to be the first function not differentiated times the derivative of the second function, so g prime of x, plus the second function not differentiated times the derivative of the first function. So we do have to differentiate both functions, but the actual derivative of the product of those two functions is a little bit more complicated than that. So the first function times the derivative of the second, plus the second function times the derivative of the first. So because we're applying multiple functions, including the derivatives of the individual functions, it'll often help to start by finding the derivatives of the individual functions before we attempt to apply the whole product rule. So when you look at your function, break it down into the two individual algebraic expressions, find their individual derivatives, and then you can plug everything into the derivative formula for this product rule. Typically with a rule like this, there will be some additional simplification that has to take place after we do the substitution with the function rules and the derivatives. And so we just go from there depending on what our derivative looks like. So let's use the product rule and let's do a couple of examples. So we want to differentiate each of the following functions. So our first function, f of x, is defined as the product of 2x plus 5 times 3x minus 4. Now, technically speaking, we could approach a function like this in a couple of different ways. We want to differentiate this function, and as of right now, it's one expression multiplied by another. So we can use the product rule, which is what we're going to do, but alternatively, another option would be to actually FOIL out this pair of multiplied binomials and then just go term by term by term. So here that would be an option to just multiply these two binomials together and then differentiate the result. But keep in mind, the more complicated the product becomes, the less likely it is that we could use an approach like this. So maybe we can do that to check our work at the end of this example. But here we're going to use the product rule, which requires us to identify each of these individual expressions as one individual expression, of course, find the derivative of each, and then plug everything into this expression for the product rule. So I'm going to take the first algebraic expression, what we're thinking of as the first function, and I'm going to start by finding its derivative. So the derivative with respect to x of 2x plus 5. Okay, so I'm going to go term by term based on the sum rule. This individual first term, if I use the power rule here, we know it has an exponent of 1, so bring that exponent down, multiply it by the coefficient, which is 2, and then decrease the exponent by 1, which will make it a 0, which makes the x go away. Okay, then if I differentiate the 5 by itself, we know the derivative of a constant function is 0. So the derivative of this expression is just going to be 2. Now I also need to differentiate the second expression. So the derivative with respect to x of 3x minus 4. Okay, so the derivative of the first term is just going to be 3 for the same reason as this one. And then the derivative of that constant 4 is going to be 0. So notice here, because of the form of our two original expressions, the derivatives were both constants. So now I'm going to use my product rule to find the derivative of this whole function. So f prime of x is defined as the first expression. Now notice here we're calling each of the individual functions f and g. Here the whole function is referred to as f. So let's just think of it as the first expression and then the second expression. However, it's going to be easiest to think of it. So in this case, the whole derivative is going to be the first expression, which is 2x plus 5, times the derivative of the second expression. Well, the derivative of that is going to be 3, plus the second expression, which is 3x minus 4, times the derivative of the first expression, which is 2. So now it's just a matter of cleaning all of this up. So we need to distribute our 3. Now notice it's behind. You can distribute from behind as well as from the front where you're probably used to distributing. So we just need to make sure 3 is multiplied by both of those terms in parentheses, and then also 2 is multiplied by both of those terms. So that's going to be 6x plus 15 plus 2 times 3x is going to be 6x. And then watch your signs here. Negative 4 times 2 is going to be negative 8. So we're adding a negative 8, or otherwise think of it as subtracting 8. Now I just need to combine my like terms. So I have 6x plus another 6x. They don't cancel, they combine. So that's going to be 12x. And then 15 minus 8 is going to be 7. So that is the value of our derivative. Now, just for the sake of checking it, again, as I mentioned at the beginning of this example, technically speaking, we could FOIL out this binomial multiplication, simplify it down, and then differentiate term by term. So let's see if we would get the same derivative if we did that. In other words, if we started by simplifying this original function and then differentiating another form of it, we should get the same answer. Let's verify that we do. So the first pair, 2x times 3x, would be 6x squared. Okay, the outer pair would be negative 8x. The inner pair, 5 times 3x is 15x. And then the last pair, 5 times negative 4, would be negative 20. And then here we just need to combine our like terms. So that's going to be 6x squared. Negative 8x plus 15x is positive 7x. And then minus 20. So if we were to differentiate this form of the function, we can use the sum and difference rules, we can use the power rule, we can use the constant rule, and then go from there. So our first term, if we take the derivative, pull down the 2, multiply it by the 6, so that'll give us a coefficient of 12, and then decrease the exponent by 1, which will give us x to the first power. For our second term, pull down the exponent of 1, multiply it by the 7, so we get a positive 7. Decrease the exponent on x by 1, which takes us to x to the 0, which eliminates the x. Okay, and then when we differentiate the constant, we know we get a derivative of 0. So this is going to be our derivative. Notice it matches exactly what we got with the product rule. If we approach a problem using two different strategies, of course, we should get the same answer. So in this case, it does make sense that the derivative has the same value. Okay, let's try another one. Now, this particular one we could also approach in the same way. Technically, we could take this first expression and distribute it into parentheses, or we can think of it as one expression multiplied by another and use the product rule to find the derivative, again, thinking of it as one expression times another. Now, if we're going to use the product rule, as before, we need to differentiate each of these expressions. So first we'll take the derivative of 4x squared. So here we're going to use the power rule. So bring down the exponent, multiply it by the pre-existing constant, which is 4. So 2 times 4 is going to give us 8. And then decrease your exponent by 1. So 2 minus 1 is going to be 1. So our derivative is going to be 8x. Differentiate the second expression. So the derivative with respect to x of x cubed plus 5x. Okay, again, power rule and then the sum rule because there's 2 terms. So bring down the 3, decrease the exponent, so 3x squared. Bring down the 1, multiply it by the 5, and then decrease the exponent so it goes from 1 to 0, the x is eliminated. So this would be our derivative in this case. So if we want to differentiate using the product rule, it's going to be the first expression, so 4x squared, and make sure you put it in parentheses. When we do substitutions, it's a good idea to substitute with parentheses around our expressions that we substitute. So our first times the derivative of the second, which in this case is going to be 3x squared plus 5, plus our second function, non-differentiated, times the derivative of the first, which is going to be 8x. Okay, now as before, we need to distribute. So the first term, we're going to distribute the factors from the front. The second term, we're going to distribute from behind. So 4x squared times 3x squared. Well, 4 times 3 is going to give me 12. And then x squared times x squared, we have 2 x's here, 2 x's here, multiply them all together, we get an x to the 4th power. 4x squared times positive 5 is positive 20x squared. Now we're adding, everything here is positive, so it's all just going to be addition from there. So x cubed times 8x is going to be 8x to the 4th power. And then 5x times 8x is going to be 40x squared. Now notice we have 2 pairs of like terms. So 2 terms with x to the 4th power, 2 terms with x squared. So let's combine all of those together. So 12x to the 4th plus 8x to the 4th is going to be 20x to the 4th. And then 20x squared plus 40x squared is going to be 60x squared. That is going to be our derivative. And again, if we wanted, we could distribute at the very beginning and then differentiate term by term just like we did here, and we will find that we end up with the same derivative in that case. Now let's look at one more, slightly more complicated, but again, we're going to approach it in the same way. Now with this particular function, we do have 2 expressions multiplied together. So the first expression would be 3 times the square root of 6 plus 2, and then the second expression would be x squared. So just like with the other 2 examples we just looked at, technically speaking, we could distribute this x squared. The issue here is when we distribute the x squared to this first term, we would have to multiply the x squared times the square root of x, which is a relatively complicated thing to do. So in this case, distributing, simplifying, and differentiating that way would probably not be the best approach. So we're going to use the product rule here. So as before, we need the derivative of each of our individual expressions. So I need the derivative of 3 times the square root of x plus 2. Okay, now if you think back to what we did with square roots, remember we don't have a rule for radicals, but we do know that we can convert a square root to a fractional exponent. So remember there's an understood 2. So x has an exponent of 1, and then the radical has an index of 2. So we can rewrite that radical as a rational exponent of 1/2, and then of course plus 2. So think of differentiating this particular version of this expression rather than the one that has the radical. So we would use the power rule for the first term, bring down your exponent. So 1/2 times 3 would be 3/2, and then decrease your exponent by 1. 1/2 minus 1 would be negative 1/2. And we're just going to leave it like that for now. Once we actually plug things into the product rule formula, we'll simplify from there if we need to. Now we need to also differentiate our second term, but the second term is a constant. We know we take the derivative and it goes to 0. So that's going to be our derivative for our first expression. The derivative with respect to x of the second expression, which is x squared, is just going to be 2x. So now let's take the derivative of the whole function using our product rule. So first function, and let's write it using that fractional exponent notation. We'll see if that helps. We'll see if it doesn't. Let's use that notation for now though. So 3x to the 1/2 plus 2. So the first expression times the derivative of the second, which would be 2x, plus the second expression, which is x squared, times the derivative of the first, which is 3/2 times x to the -1/2. Okay, so now we need to clean all of this up. So here, this 2x needs to be distributed. Now, what's going to happen with the exponent when we distribute it? I want to go ahead and write this with an exponent of 1. Normally we don't write it, it's understood, it's implied, but I want to write it because we're going to need it in just a moment. Okay. So as we clean this up, 2 times 3 is going to give me 6. Okay, now what about the x's though? So I have an x to the 1/2 and an x to the first power. The general rule is when we multiply two powers with the same base, we can add their exponents together. So if I were to take 1/2 and add 1, let's go out to the side. If you need, you can go out to the side and do this. So 1/2 plus 1. Well, of course, I would need to get a common denominator to do this addition. We don't want to write this as 1.5. We want to write it as an improper fraction. So that's going to be 1/2 plus 2/2, which is going to give me 3/2. So when I multiply the x's together, add their exponents, that's going to give me x to the 3/2. And notice if we use the radical version of this expression, doing that multiplication would not have necessarily resulted in this fractional exponent, whereas here we can actually combine them together and have one simplified term. Then we also have positive 2 times the 2x, so plus 4x, and that's going to be everything from our first pair. Next one, x squared times 3/2 times x to the -1/2. Okay, now notice this is just one term, two factors multiplied together. So we just need to clean up this multiplication. Now, first off, we do know it's going to be an addition because both terms or both factors are positive. So we have a coefficient of 3/2. And then just like before, we have two x's, two exponents. The bases are the same, so we're going to add their exponents together. So 2 plus -1/2, or 2 minus 1/2, if you want to think of it that way. Get your common denominator. So we need a denominator of 2. So 2 is going to become 4/2 minus 1/2, and that is going to give us 3/2. So be careful here. We have a coefficient of 3/2, and then we also have x to the 3/2 power. So it's repeated, but they are different. They do mean something different. All we have to do now is add together any like terms that we have. So notice we do have two terms with x to the 3/2 power. So anytime we have the same variable and the same exponent, those are considered to be like terms. So we have 6x to the 3/2 and 3/2 x to the 3/2. So if we combine those two together, it's going to be a coefficient of whatever 6 plus 3/2 is. So it might again be beneficial to go to the side and just work that out to see what that coefficient is going to be. Okay, again, we need that common denominator. So 6 with a denominator of 2 could be rewritten as 12/2. So 12/2 plus 3/2 is going to be 15/2. So we have 15/2 times that common factor, x to the 3/2 plus 4x. And that is going to be our derivative. So notice here, these three functions we looked at were significantly more complicated than the functions we looked at in the last video when we just had the sum and difference rule and the power rule. So adding on the product rule is going to allow us to deal with slightly more complicated situations. And of course, within the use of the product rule, notice we use the power rule, we use the constant rule. So you're going to end up layering all of these rules. The product rule, the quotient rule are going to be for more complicated situations, but because they're each going to require individual derivatives, those individual derivatives of the individual expressions, that'll again allow us to use our other rules like the power rule, like the constant rule, those kinds of things. Okay, so that's what happens with a product. So again, just to reiterate, it's going to be your first expression times the derivative of the second plus the second expression times the derivative of the first. Whatever that ends up being, simplify it all down and that's going to be your derivative. Now what about the quotient rule? Well, just like with the product rule, we can't oversimplify it. So the derivative of a quotient is not the quotient of the derivatives. That idea is specific to the sum and difference rule. When we have multiplication or division, unfortunately, we can't just distribute the differentiation operator, if you want to think of it that way. So here's the quotient rule. So given two functions, f of x and g of x, the goal is to take the derivative with respect to x of the quotient of those two functions, and we're specifically going to differentiate f of x over g of x. And keep in mind, if we flipped the order, we would just flip the order for the expression that I'm about to write. So when we differentiate the quotient of two functions, it's going to be the lower function, g of x, times the derivative of the upper function, so f prime of x, minus the upper function times the derivative of the lower function. And then we're also going to have a denominator, so all of this is then divided by the lower function, what we're calling g of x, squared. So far and away, this is the most complicated formula we have. Okay. Now, how do you remember this formula? I have kind of a shorter way for you to remember it. So at lower function times the derivative of the upper function minus the upper function times the derivative of the lower function all over the lower function squared. So the way I remember this is low d high minus high d low all over low squared. This is a phrase that you can repeat in your head when you're trying to differentiate a function that involves a quotient. So low d high, derivative of the upper function, low d high minus high d low, derivative of the lower function, all over low squared. So you want to practice with this phrase. Make sure you can memorize this phrase, because once you have that phrase memorized, that's going to tell you what this formula looks like. It's going to determine all the different pieces you need in order to evaluate this particular derivative. So notice within this derivative, just like within the product rule, we do have derivatives of the individual constituent functions. So just like with the product rule, it's a good idea to start by looking at each of the expressions by itself and differentiating each of them individually. So let's start with the upper function. So we want to take the derivative with respect to x of our upper function or upper expression. So we're taking the derivative with respect to x of 1 plus x squared. Okay, the derivative of our first term, a constant, is 0. The derivative of the second term is going to be 2x. the derivative of the lower function, which is x cubed plus 1. Take the derivative of the first term, so that's going to be 3x squared. And then the derivative of the second term, again, that's a constant. We differentiate it, it goes to 0. So this is going to be d high, if we're using that acronym, or that mnemonic, and this will be d low. So when we take our derivative, f prime of x, it's going to be low, so our lower function, again, substitute with parentheses around it. So low d high, which is 2x, minus high, which is 1 plus x squared, d low times the derivative of the lower function, so 3x squared, all of that divided by the lower function squared. So x cubed plus 1 quantity squared. So here we have a couple things to simplify, but how far we simplify is really just going to depend on the situation we're in. In most cases, when you apply the quotient rule, it's appropriate to just leave the denominator as is, particularly if your denominator came from a function that has more than one term. So rather than actually distributing all of this, in other words, squaring that binomial, typically we can just leave that denominator in that form, in that factored form, and that will be completely acceptable. But again, it's really just going to depend on the situation. Ultimately, it boils down to how much can you simplify. So anytime we have a numerator and a denominator, there's always the possibility of having common factors in each that can reduce to 1. In other words, if there's anything on top that would cancel with something in the denominator, then we want our derivative to be in such a form that we could identify those things that cancel and in fact cancel them out. But for now, you want to leave that denominator alone until you potentially get to the point where you could do that. So just focus on what's going on in the numerator. We want to clean up the numerator. So that's going to involve distribution just like it did with the product rule. Be careful though when you distribute, because keep in mind the second term in which you're distributing is subtracted, so you'll have to make sure that negative sign is distributed as well. So for the first pair, we have x cubed times 2x, so that's going to be 2x to the 4th power. 1 times 2x is going to be positive 2x. Okay, now over here, again, be careful. We're going to distribute the negative as well as the 3x squared. So 1 times 3x squared times negative 1. That's going to be negative 3x squared. And then x squared times 3x squared times negative 1. Again, the term is going to be negative. And then 3x squared times x squared is going to be 3x to the 4th power. And then again, don't forget your denominator, but leave it in this factored form. Okay, I'm going to come over here. Notice in this numerator, we have two like terms. We can combine those. So 2x to the 4th minus 3x to the 4th is going to be negative x to the 4th. And then if we write in the standard order, which will be highest exponents to lowest exponents, our next term would be the negative 3x squared. And then our final term would be positive 2x. All of that divided by x cubed plus 1 quantity squared. Now, do we need to do anything with the denominator, or are we done? What I want you to focus on now is what additional could you do with the numerator. So you can't combine any more terms in the numerator. There aren't any more like terms. But keep in mind, the numerator could still potentially be factored. So notice all three terms in the numerator have a factor of x in common. So technically we could factor out an x from each of these. If we factored out an x here, we'd be left with negative x cubed. Here we'd be left with negative 3x. Here we'd be left with 2. And then again, we'd have that greatest common factor of x factored out front. The reason we don't need to do that here is because if you picture what you would be left with, it cannot cancel with a factor of x cubed plus 1. The general rule with reducing a rational expression is you have to have complete factors that match. So the only thing that could reduce with something in the denominator would be an x cubed plus 1 verbatim, only an x cubed plus 1. Because factoring out that x from the numerator would not result in x cubed plus 1, that's our indication that factoring here won't do anything, doing anything with the denominator won't do anything. This is ultimately the simplest form we can get. There won't be anything else we can do to reduce anything any further. So that's an indication that we can leave the denominator as is without running into any problems, without saying that this could be simplified further, because in this case it can't be simplified further. Now notice in this case this derivative is quite a bit more complex than the derivatives we've seen before, but it makes sense because the function we started with was more complex than what we've seen before. So the more complicated your original function is, in most cases the derivative will be correspondingly complex. Okay, let's try another example. Okay. So again, we have a quotient of two algebraic expressions. We want to differentiate this function, so we're going to use our quotient rule. We're going to start by finding the derivatives of your individual constituent algebraic operations. So the derivative of the numerator, so the derivative of x squared minus 3x. Okay, derivative of the first term is 2x. Derivative of the second term is negative 3. So this is what we'll call d high. This is our upper derivative. And then we also need to differentiate our denominator, which is x minus 1. Okay, the derivative of the first term, x to the first power, will bring down the 1. So we now have a coefficient of 1, which wasn't written before, but we do want to write it now because it will now be x to the 0 power, which means the x goes away. So there's the 1. And then we differentiate the constant and it goes to 0. So this is going to be our d low. So low d high minus high d low all over low squared. So low, so g prime of x is low, which is x minus 1, d high, which is 2x minus 3, minus high, x squared minus 3x, d low, which is 1, all over low squared, so x minus 1 quantity squared. Okay, again, leave the denominator alone, at least for the time being. We want to focus on cleaning up the numerator. Okay, so the first pair, we have to FOIL that out. That's 4 multiplications represented right there. So x times 2x is going to be 2x squared. Now let's see if we can do the outer and the inner at one time, because they will be like terms. So x times negative 3 is negative 3x. Negative 1 times 2x is negative 2x. So negative 3x plus negative 2x is going to be negative 5x. And then our last pair, negative 1 times negative 3, is going to be positive 3. Now we lucked out over here because notice we're just multiplying by 1, which won't change anything. So all we need to do is distribute that subtraction. So minus x squared, and then notice here we're distributing it to a pre-existing subtraction, so negative and negative combines to give us a positive, so plus 3x. Again, leave your denominator alone, at least for the time being. Okay, do we have any like terms? Well, we've got 2 terms with an x squared. We've got 2 linear terms. So let's combine those together. So 2x squared minus x squared is going to be a single x squared. Negative 5x plus 3x is going to be negative 2x plus 3. All divided by x minus 1 squared. Are we done? Are we not done? Well, the numerator can't be simplified any further in terms of combining like terms. But again, we need to explore the option that potentially, if the numerator were in a factored form, it might reduce one of the factors in the denominator. So to be sure, let's go over to the side and let's just look at the numerator by itself. We need to see if this numerator factors. Does it factor? Well, if it does, we're looking for numbers that would multiply to give positive 3 and also add to give negative 2. So you might initially be thinking 3 times 1. Well, the only reason 3 times 1 doesn't work is, keep in mind, because they multiply to give a positive, that just means they have to have the same sign. So it's either going to be positive 3 and positive 1, or negative 3 and negative 1. If we combine positive 3 and positive 1 together, we get a positive 4. If we combine negative 3 and negative 1 together, we get a negative 4. Neither of which matches up with our coefficient on our linear term. So because none of the factorizations of 3 would result in an addition that adds up to negative 2, that's our indication that this does not factor. This trinomial does not factor. Which means that there will not be anything to cancel with one of our x minus 1's in the denominator. So there's nothing we can do. That would be as far as we go. Now suppose this had been something that factored. If it had been something that factored, then we would want to explore the factorization. If the factorization in fact contained an x minus 1, then that would represent a common factor that we could reduce from the numerator and denominator. So we do want to explore that possibility, because in some cases the derivative may result in something like that, some type of expression where the numerator and denominator have something in common and we can reduce it. We always want to report fractions and rational expressions in lowest terms, which means any common factors should be divided out. That's always going to be considered best practice. So let's finish with an application specifically for the quotient rule. So this is a business-based application. So business speaking in terms of a profit-based business. Businesses are often interested in monitoring their costs, what it takes to produce their products or services, their revenues, in other words, what they bring in by selling their products and or services, and of course the difference between the two, the bottom line, what we call profit. Okay, now there's two ways of thinking about these three quantities. We can think in terms of accumulated values. In other words, imagine a single day of running your business. You accumulate costs for the day. Hopefully you accumulated some revenue for the day, which means you have an overall profit for the day. So accumulated values, total cost, total revenue, total profit, are often represented as functions. We typically label them with the capital letter corresponding to C, R, and P. So C of X for cost, R of X for revenue, and P of X for profit. And keep in mind, profit is always going to be defined as your revenue minus your cost. So profit is usually not independent of the other two. Typically we take our revenue function, the money we've made, and subtract the cost function, cost for producing and selling, and then the difference between the two is defined as our profit. Of course, if it's a positive number, that means we've made money. If it's a negative number, that means our costs are higher than our revenue and we're losing money. Now, those are going to be important to monitor, but due to different economic factors, the amount often varies from item to item. In other words, the 10th item may ultimately cost more. It's possible that the 10th item we produce and sell costs more to produce than, for instance, the 1000th item. It's called an economy of scale. In a lot of situations, the more and more we produce and sell, overall our costs are going to decrease over time. So rather than focusing on accumulation, where maybe the first item we produce and then the 100th item we produce vary a lot in terms of what they cost, we may focus on average amounts. So what's the average cost? If the first item costs a lot to produce, but the 100th item doesn't cost nearly as much, well, what's the average between the two? focusing on the average may give us a better overall picture than just focusing on the total cost overall. So the average functions can be defined for each of these three original functions if we take the total cost for however many items we produce and sell, and divide by how many items we produced or sold. So total cost for instance, 5 items divided across those 5 items would represent our average cost. And of course, that can be for any x value we want, specifically when we think of x as an integer if we're talking about individual items being produced and sold. So our average functions for cost, the average function will be c of x divided by x. For revenue, same kind of thing, but we're using our revenue function instead. So r of x divided by x. And for profit, that's going to be p of x divided by x. Why does this factor into this particular section where we're discussing differentiating using the product rule and using the quotient rule? Well, the reason this fits here is because these are now rational functions. What was previously a function that maybe didn't involve a product or a quotient, now by default, just based on the structure of each of these 3 average functions, we've taken a function and divided it by another algebraic expression, essentially creating something where if we wanted to differentiate it, we would have to differentiate it using the quotient rule, using the fact that there is a numerator and there is a denominator. So what might it look like in terms of an application where we want to take the derivative of one of these functions? Let's look at an example. Okay, so a skateboard manufacturer has found that the cost in dollars of producing X skateboards is given by C of X is equal to 900 plus 18 times X to the 0.7 power. And again, X is going to be the number of skateboards produced. And the revenue from the sale of the same number of skateboards is given by R of X is equal to 75 times X to the 0.8 power. We want to find the rate, keyword rate, I'm going to underline that, that's going to be important. We want to find the rate at which the average profit per skateboard is changing, so the rate of change of the average profit when 20 skateboards have been built and sold. So there are some layers to this problem. What we want to determine is, based on our average profit, based on how much we make on average for each individual skateboard we make and sell, how fast is that profit changing? It could be decreasing, it could be increasing. How fast is that profit changing at the moment when we've produced and sold 20 skateboards? In other words, once we go from our 19th to our 20th and then our 20th to our 21st, at that single point, that single level of production, how is our average profit changing? Again, either increasing or decreasing. Well, we're looking for several things here, which means we have to approach this in layers. First thing we need in order to find a rate of change, anytime you see that word rate of change, think derivative. Since we're looking for the rate of change not over an interval, not for producing maybe the 20th to the 25th skateboard. That would be the average change from the 20th to the 25th. We're looking for the rate of change at that exact moment when we're only producing and selling 20 skateboards. So that means we're talking about the derivative. That represents the instantaneous rate of change. Well, we want the derivative of the average profit. Now remember, average profit has a couple different layers to it. It's defined as the profit, the total profit, divided by the number of items that we've produced and sold. But the profit function itself is always defined as our revenue, the money we've made, minus our costs. In other words, how much it takes to produce and sell. So if we want to find the average profit First thing we need to do is find the total profit. We haven't been given a function for that. We've been given a function for cost, and we've been given a function for revenue. So the difference between these two functions is what we're going to think of as total profit. Now, it's not quite average profit, but it's a good start. So our profit function, by definition, is defined as our revenue function minus our cost function. Well, here we can sub in the algebraic expressions for each of these. So revenue is defined as 75 times x to the 0.8 power. And then cost, which we're subtracting, is going to be 900, which would represent our fixed cost, plus 18 times x to the 0.7 power. So keep in mind, even if we produced and sold 0 items, which means this term would go away, we would still have $900 worth of cost, which would be what it takes to keep the lights on, to pay executives, to pay for advertising, those kinds of things that are not specifically dependent on how much we produce. So once we combine all of this together, clean it up, it's going to be 75 times x to the 0.8 power. And if we list in order, the next term we'd want to write would be the term with x to the 0.7 power. It's being subtracted, so it'll be a negative term. So minus 18 times x to the 0.7 power minus 900. So that is going to be our total profit. So if we knew how many items we produced and sold, in this case we're producing and selling 20 skateboards, if we wanted to know the total amount of profit that we've made for producing and selling 20 skateboards, we would just plug in 20 to this function, and that would give us our total profit. Now we're interested in the average profit, which is defined as the profit function divided by the number of items we produced and sold. So if we take the total profit and distribute it over the number of items that we've produced and sold, that's going to be the average profit per item. So 75 times x to the 0.8 power minus 18 times x to the 0.7 minus 900, and then we're dividing all of that by x. So that's our average profit function. So if we were to plug in 20 in this case, that would tell us we've made a certain amount in total. We divide it over the 20 items we've produced, and so the amount we come up with would be the average profit we make per skateboard. Of course, keep in mind, the first skateboard we may not make as much money off of that as we do the 20th, but we're distributing the total profit across all 20 items, regardless of the actual profit per item. Now, what we're ultimately interested in is the rate of change, the rate at which this amount, this expression, is changing at the moment when 20 skateboards have been built and sold. So as soon as we see rate of change at a single point, at a single value of x, that means we're taking our derivative. So we are taking the derivative with respect to x of our average profit function, which is going to be this function. And I'm just going to sub in the actual function expression. So 75 times x to the 0.8 minus 18 times x to the 0.7 minus 900 divided by x. Okay, so this is what we want to find. This is the derivative we want to find. And again, the reason it fits into this particular section is because if we want to differentiate a function like this that has a numerator and denominator, we know now that we need the quotient rule. So based on the quotient rule, we know we're going to need the derivative of the upper function and the derivative of the lower function. So let's look at those individually. So the derivative with respect to x of our upper function, which is 75 times x to the 0.8 minus 18 times x to the 0.7 minus 900. Okay, what's that going to be? So we can go term by term. Each term is subtracted. And then we're going to use the power rule for each of these. So bring down your exponent, multiply it by the coefficient. So let's see what that's going to be. So 75 times 0.8, it's going to be a coefficient of 60. So 60 times x to the 0.8 minus 1. So let's verify that. 0.8 minus 1 will be the negative 0.2 power. And we know for a final answer we don't want negative exponents, but here we're still in the middle of the problem, so we're just going to leave it as a negative exponent for now. Same thing for the next term. Bring down the exponent. It's going to be a negative term. So 18 times 0.7 is going to give us 12.6 times x to the 0.7 minus 1. So 0.7 minus 1, which is going to be negative 0.3. And then our last term is a constant. We know when we differentiate that constant, it goes to 0. So this is going to be the derivative of our upper function, what we're calling d high. Using that little mnemonic, that's d high. Now we also need the derivative of our lower function. So the derivative with respect to x of x. So differentiating this, remember, has an exponent of 1. We bring down the exponent, decrease the exponent by 1. So our derivative is just going to be 1. I didn't leave enough space, I don't think, so I'm going to come down here and actually perform the derivative calculation. So based on the quotient rule, low d high minus high d low all over low squared. And again, let me label this one. That's d low. So low, which is x, d high, which is what we calculated here. So 60 times x to the negative 0.2 power minus 12.6 times x to the negative 0.3 power. So low d high minus high 75 x to the 0.8 power minus 18 x to the 0.7 power minus 900 high d low, which is 1, all over big fraction bar, all over low squared, so x squared. Okay, let's just clean all of that up. Now notice this second part, we're just multiplying by 1, so nothing special happens there. We do need to distribute the x for the first pair though. So x times 60, x to the negative 0.2. Well, first off, the coefficient will be 60. And then we have x to the first power times x to the negative 0.2. So because the bases are the same, we're adding our exponents. So 1 plus negative 0.2 is going to be positive 0.8. Okay, next term. Negative times a positive will be negative, and our coefficient is going to be 12.6. And then we have x to the first times x to the negative 0.3. Again, the bases are the same, so we add the exponents. 1 plus negative 0.3 is going to be positive 0.7. And then all we need to do over here, again, because we're multiplying by 1, is distribute that negative sign. So the first term will go negative, the other two will go positive. So minus 75x to the 0.8 plus 18x to the 0.7 plus 900. And don't forget, after all that work, that you still have a denominator, which is x squared. Now, believe it or not, after all of that, we have some like terms. So we have two terms that have x to the, oops, I left off my x. That's better. Okay, we have two terms that have x to the 0.8 power. There we go, those are the two terms. And then two terms that have x to the 0.7 power. So those pairs can combine, and then the 900 just kind of hangs out. So 60 minus 75 is going to be negative 15 x to the 0.8, negative 12.6 plus 18, let's just verify it in the calculator, negative 12.6 plus 18, it's going going to be 5.4, positive 5.4, so plus 5.4 x to the 0.7 power plus 900 divided by x squared. And so that's going to be as far as we can go. Now, it's tempting to try to cancel these x's. It does not happen, right? We have to be able to cancel a factor from the entire numerator with something from the denominator. So because we don't have a whole x in common among these three terms, there's nothing that can reduce with that x squared in the denominator. So that's as far as we're going to go. Well, we're not quite there. Let's revisit the prompt, what we were looking for. We were looking for the rate of change of average profit. Okay, we just found that, so the value of the derivative, the formula for the derivative, this represents the rate of change of average profit. But we want to know what is the value, what's the actual value of that expression when 20 skateboards have been built and sold. In other words, when x is 20. So now we want to evaluate at x equals 20. What's the rate of change at that specific point based on that specific production level? So let's see. So that's going to be negative 15 times 20 to the 0.8 power plus 5.4 times 20 to the 0.7 power plus 900 divided by 20 squared. Now, of course, we will do this in the calculator, but how you approach this, you've got a couple of different options. You can technically type this whole expression in one line if you want, but if you do that, you need to make sure there are parentheses around your numerator and around your denominator. Alternatively, you can just go one term at a time. So if, for instance, evaluate this first term, and then hit enter, and then add on the second term, hit enter, add on 900, hit enter, and then divide by 20 squared, which, let's go ahead and simplify that, that's going to be 400. So let's do that approach, because again, if you forget those parentheses in the numerator, you will get a different answer than what you're intended to get, because you're not actually evaluating what this expression is telling you to evaluate. So if we wanted to go one term at a time, I'm literally just going to type in the first term, which would be negative 15 times 20 raised to the 0.8 power. Okay, so that's our first term. Now notice it's got a long decimal, and we're going to round at the end, but for now we're not rounding, we're just building on one term at a time. So to that term we are adding 5.4 times 20 raised to the 0.7 power. And keep in mind, your calculator understands order of operations, so it knows to apply the exponent, then do the multiplication, and then add those two terms together. So then I'm going to press enter, and there I am so far. Notice it's still a negative number, but when I add 900 to that, it's now going to be a positive number. Now I'm not quite finished. That's my numerator. I still need to divide that by 20 squared, which is 400. And it says, if necessary, round to the nearest cent. So here we're talking about a dollar amount, but not quite just a dollar amount. So cents means 2 decimal places. So that's $1.95. Okay. But that's not quite it, because we have to think about what we just found. This is the rate of change of average profit. So what's changing? Well, profit is represented by dollars, but when we talk about average profit, it's dollars divided by units, how much we're producing. So when we're talking about how this particular value is changing, it's the dollar amount worth of change per unit produced. So it's $1.95, but not quite $1.95. It's $1.95 per unit. In other words, per skateboard. So anytime we're talking about a rate has a unit that's going to be fractional. So here the unit is dollars per unit. So in other words, at that single point, at that single level of production, this is how our profit is changing. So as we produce our 21st unit, we have something roughly like that, increasing our profit to go from our 20th to our 21st unit, close to that. So that gives you an example of how you might actually use the quotient rule in a real situation, in an applied situation. Keep in mind, derivatives are very much applicable to the real world. In the real world, things are changing all the time. Values are not fixed. We're talking about change. Things are always changing. The derivative is a great way to explain how things are changing if we want to zoom in and look at change at a very, very small level, how things are changing at an instantaneously small level as we go, for instance, from one unit of production to another. So in the next video, we'll have one additional derivative rule that we're going to add to our list that's going to let us deal with one additional situation that we haven't looked at. So we know how to differentiate something with a power. We know how to differentiate across addition and subtraction. Now we know how to differentiate anytime a function involves a product or involves a quotient.